Hi, this is Mrs. Jacobs. I'm here to give you a tutorial about how to draw an IFF chart for momentum problems. And we do have a sample problem here that we're going to solve. So first of all, IFF stands for initial momentum. The symbol for that is P0, subscript 0. P is the symbol for momentum, 0 means initial. The second F stands for final momentum. And that symbol is just P. The middle F stands for force. So it's sort of like, what is the force that is changing the momentum? Okay. Every IFF chart is going to have three graphs. The first graph is the I. It's the initial momentum, the P0. So because it's a momentum graph, you need mass on the x-axis and velocity on the y-axis because mass times velocity is momentum. And you've got positives and negative momentums. Sorry, positive and negative velocities, and you could have positive or negative momentums. The last one is also a momentum graph, P final. So that's going to be velocity on the x-axis, y-axis again, and mass on the x-axis. The middle graph is the force graph, and it's a force versus time graph. But again, the force could be positive to the right or negative to the left. Okay, so basically there's three graphs that we're going to be filling in. The most important thing about these graphs is that graph number 1, P0, whatever area we get on this graph, plus the area we get on the second graph, which is called delta P, change in momentum, has to equal the area that we get on the final graph. So our overall equation is always going to be initial momentum plus the change equals the final momentum. And that is true no matter what standard you're working on, whether it's an impulse problem, standard 1, or a conservation of momentum problem, standard 2. Okay, so how do we fill in this chart? Well, let's do it with a sample problem. It says, a 300-gram tennis ball moving at 25 meters per second gets hit by a racket and turns around, moving at 30 meters per second. If the collision time between the ball and the racket is 0.25 seconds, what is the force between the racket and the ball? So I was given an initial velocity and final velocity back. First, I'm going to draw the picture of the situation. So I got a tennis ball. Initially, it's moving at 25 meters per second. Then gets hit with our racket. Okay. And the ball turns around and it's moving the opposite way, 30 meters per second. So they didn't give me positive or negative in front of these, but one of them has to be negative because it's changing direction. It doesn't, the way I drew it, the second one would be negative because it's to the left. Okay. If you chose it the other way around, it doesn't matter. You're still going to be able to solve the problem and get a correct solution. So we know the initial velocity, V0, is 25 and V final is negative 30. Okay. We also know that the mass is 300 grams, but we can't use grams in our momentum problems. We have to use kilograms. So I divide by 1,000, that's 0.3 kilograms. Okay. And now I have enough information. I have a mass and I have two velocities. That's enough information to fill out the initial and the final momentum graphs. So I'm going to say my mass is 0.3 kilograms on the x-axis. And I'm putting that for both graphs because that mass doesn't change. What does change is the velocity. It was initially positive 25 meters per second. And we'll be finding that area in a little bit. That area is the momentum. And then the negative velocity has to be down here below the x-axis. And that's negative 30 meters per second for velocity. So you can see the momentum has gone from pretty high positive to pretty high negative. Okay. The other thing I was given the collision time, but I was not given the collision force. That's our unknown. There will always be one thing on a graph that I don't know. So I was given that the collision time was 0.25 seconds. So I'm going to put that on the x-axis. I don't know the force. That's what I'm going to solve for. However, I do know that the force has to be to the left, because the only way for the ball to turn around and move to the left is for the racket to hit to the left. So the force has to be way down here. It's some kind of negative number of newtons. Okay. The other thing that has to make sense is, again, area 1 plus area 2 has to equal area 3. If this final area is negative and I start off with a positive area, the only way to get from positive to negative is to have a middle graph that is negative, more negative than this was positive, to end up with a negative area at the end. Okay, so I'm going to write P0 plus delta P equals P final. Again, this is area 1. Uh-oh, looks like I'm out of lead. Oh, we're good. Area 1 plus area 2 has to equal area 3. So we're going to do mass times velocity for this one. That's momentum. 0.3 kilograms times positive 25 meters per second. Plus force, which is unknown, times time. That's the area of the second graph, force times time. So I got my unknown force, I got my time, equals area 3. This is going to be, again, mass times velocity. The mass is not different, but the velocity is now negative 30 meters per second. Okay, and now it's an algebra problem where I'm solving for force. Move this down here. Let's solve this problem together. I actually did not come prepared with a calculator. Let's see if I have one. Yes. Okay. So 0.3 times 25 is positive 7.5 kilograms meters per second is the unit. Nothing cancels there. Plus F times 0.25 equals 0.3 times 30 is negative 9 kilograms meters per second. So here I'm going to subtract 7.5 from both sides. So I get F times 0.25 equals negative 16.5 kilograms meters per second. And I'm dividing both sides by 0.25 seconds. It's okay. If the units are confusing you, it's okay if you just have the units up here. I'm okay if you have the units up here in your initial equation and you just drop them off when you do the algebra. It's not a big deal to me. So 16.5 divided by 0.25 is negative 66. And because I'm solving for force, the answer is newtons. You might say, how do I get a newton? A newton is a kilogram times meter per second divided by a second. That equals a newton. Okay. And I don't necessarily expect you to know that, but I do expect you to know that force is measured in newtons. Okay. And that's why we have to do kilograms in these problems, because the only way to get newtons is to have kilograms in the problem, not grams. So that's an example of how to set up the IFF chart visually and how to use the 3 areas to solve for an unknown. Now, this had an unknown force. The problem could have said, this is the force, solve for the time. And then this would have been t. Or the problem could have said, this is the force and this is the time, but the final velocity is unknown. Okay? And then I would know F, I would know t, but I wouldn't know this final velocity. So there will always be one unknown in your equation. But again, the overall theme is initial area plus change in momentum. Initial momentum plus change in momentum equals final momentum. And this is a good way to visualize what's happening with momentum. And the hardest thing is momentum has direction. So it does matter whether something's positive or negative. It totally changes your answer if you do it differently. Let me know if you have any questions. Talk to me in class.